So this is a super simple lab, but one that you can get some pretty neat diagrams with. What you're going to need is a bottle of water that you've marked distances off with, and a couple of paper clips and a rubber band. The rubber band is what we're going to be measuring the material properties of. You can suspend this from like a doorknob or any kind of a hook. Get a ruler behind it, measure the original length, and then you're just going to slowly fill it up with water. So you'll fill it up to each of those marks that you made on the side of the bottle. And every time you fill it with a little bit more water, you're going to measure how far out it's stretched. You'll also measure the cross-sectional area of your rubber band. Collect data to create a stress-strain graph where stress is the applied force over the cross-sectional area of both halves of your rubber band, and strain is change in length over the original length of your rubber band. Okay, so what I'm going to have you do is set up an Excel file to record all of your data and then calculate your stress-strain diagrams from your data. For each experiment, just record everything about it. So what was the temperature, what kind of rubber band did you use, any information that you're going to need, the density of water, that's going to get you the force for your stress, the original length of your rubber band, that is going to give you the information you need for calculating strain. And let's see, you'll also need the cross-sectional area of your rubber band. If you just have one of those see-through rulers, you can put the rubber band up against a see-through ruler and see that cross-sectional area. Make sure you record the units on all of these guys too. Eventually, it's good to have meters and kilograms instead of grams and centimeters, just what kind of the standard is. Okay, so I'm going to put those numbers over here so we can use them later on in our calculations. And let's see, go ahead and center those guys, I guess. So the next one, for the stress-strain diagram, Excel, when it makes graphs, the very first column that's on there, that's what it's going to put in the x-axis. And strain is what traditionally goes on the x-axis, so I'm going to make a column for strain. And the next column I'll make is for stress. That'll be on our y-axis. But before we get there, we have to kind of calculate what our length is and change in length, and we need to figure out our force. And to get the force, we're going to do that from how deep the water is, and then go from how deep it is to the volume of water, and then get the mass of the water, and then F equals ma. Have you had that before? Mass times acceleration. So we're going to just multiply kilograms by 9.81 meters per second squared, and that'll get us our force. So as we did this experiment, and you can just hand write this data down as you're doing it, I recorded how long the rubber band was stretched out. So it started at only 7 centimeters, and then as I slowly add water, I recorded both how much water was added and how much the rubber band was stretched out for that water. So this is just the centimeters that the rubber band had stretched out. But we need the change in length, not just the total length. So the change in length is that original length minus 7. So we're just looking at how much the length has changed here, taking the difference to 7. Okay, so the next column up, let's go ahead and just do a little bit of formatting here. So I'm going to highlight my cells, add some borders, add some thick borders around to the title, and make sure in your table you're recording all of the units for this thing, and that everything's real clear of what those numbers mean. Okay, so centimeters of water. And there's the volume. So most water bottles, they're just a cylinder. See if you can find a water bottle that is just a nice, straight, simple cylinder shape, because that'll help you get those volumes a lot easier. And I guess, yeah, whenever you can type in equation instead of numbers, do that. So dl is just L minus that original 7. If you double click on the lower right-hand corner, it'll automatically copy those equations down for you. Okay, so those are the centimeters of water that created those stretched out lengths. The more data points you get, the better. So fill it up with pretty small increments of water and you'll get a little bit better results. Okay, so volume, I'm just using the volume of a cylinder. So pi r squared h, my water bottle is about 3 centimeter radius. And I'm multiplying it by that column E for the height. Okay, the mass of the water, just use density to get the mass. So volume times density is equal to the mass. Copy that one down, and then force is going to be mass times acceleration. So I'm going to just click on my mass and times 9.81 meters per second squared, and that's the unit of Newton, and Newton is a kilogram meter per second squared. Our strain is actually unitless. That change in length over length, you just have to make sure that it's centimeters over centimeters or inch over inch, just so long as it's the same unit on the top and the bottom of that, you're good. And then stress is force over area. So if we're using newtons, kilograms per meter squared, make sure your area is in meters squared as well. Okay, so now we have our table, and really it was just those first two columns that we need to make that stress strain diagram of. Insert a scatter plot, and if something looks fishy in your data, just start going through the points, see which one you typed in wrong. You should also have several people take the same data and see if you can get some repeatable results. So try and eliminate errors and go for repeatability, and have a couple people take the same data from the same rubber band and see if everybody's getting the same slope. Make sure you don't have any unit mistakes on there. Okay, so it looks like it's pretty linear. If you click on the plus, you can add axis titles. So that's good practice to just always label everything. So there is our stress, force over area, and strain, change in length over length. And if we had loaded this all the way up to where it would break, we would see that the end of this graph is not linear. But for this little chunk of it, you can right-click, add trend line, and show just that nice linear trend on it. And this, if you hit display equation on chart, that will give us a nice slope that we can compare for the different scenarios in the future. Okay, so once you have one table set up for one scenario, yeah, make sure you have everything labeled. So this is the room temperature case. And the next one, let's see here. Okay, yeah, so get everything labeled. And then you can go up to the top. If you click at the very top, Control C copies it, and then Control V will paste it. So for the next scenario, just clear out your original data. And really, I guess you didn't have to clear out all of that, just your L and your centimeters of water, and then all the other formulas are the same. But what you want to do is calculate this not just for room temperature, but maybe throw the rubber band in the freezer for a while and see if, when it's cold, how that's going to change those strength properties. Or throw the rubber band in a pot of boiling water for a while and then test the same thing when it's warm and see what that does to that stress strain curve. And this is important information to know, because rubber is a very commonly used material, and it's important to know that, you know, if it's a really hot summer day or cold out in the winter, and that rubber is going to have very different strength characteristics, that's important to know. Okay, hope that wasn't too confusing. Let me know if you need help with anything, and I look forward to seeing your results.